For centuries, we expected galaxies to obey the same laws as our solar system. Stars near the edge should crawl, not race. Yet when astronomers actually measured their motions, galaxies broke every rule we understood. The speeds were impossibly high, visible matter could not account for them, and the universe's hidden mass, what would become known as dark matter, upended everything. How did we discover a dark presence shaping every galaxy, and what made the evidence undeniable? In the solar system, planets closer to the Sun whip around in tight, fast orbits, while those farther out move more slowly. This pattern fits our instincts. Gravity weakens with distance, so outer worlds drift in wide, gentle arcs. Astronomers expected galaxies to obey the same rule. If most of a galaxy's mass is packed near its center, the stars at the edge should crawl, not sprint. To test this, astronomers created rotation curves, graphs that plot how fast stars orbit at different distances from a galaxy's core. The expectation was simple. The farther from the center, the slower the orbit, following what is called a Keplerian decline. But when these curves were measured in spiral galaxies, something astonishing appeared. Instead of dropping off, the speed stayed flat. Even far from the center, stars kept racing along at hundreds of kilometers per second. The visible matter, stars, gas, and dust could not possibly provide enough gravity to hold these outer stars in place. This left astronomers with a stark choice. Either the laws of gravity change on galactic scales, or there is far more mass in every galaxy than meets the eye. Once again, science found something invisible by its effects. The way we notice wind by watching trees sway, or infer a hidden planet from the wobble of a distant star. The universe was hiding something massive, and the evidence was written in the orbits of its stars. By the early 1930s, astronomers were learning to measure the speeds of galaxies by collecting their light and breaking it into spectra. These Doppler shifts, tiny changes in wavelength, revealed how fast galaxies moved through space. At Caltech, Fritz Zwicky turned this new technique toward the Coma cluster, a dense swarm of galaxies about 321 million light-years away. He used the virial theorem, a tool that relates the random motions of galaxies to the mass needed to keep the cluster bound. Zwicky found that the galaxies in Coma were moving so quickly, with velocity dispersions around 1,000 kilometers per second, that the cluster should have flown apart long ago unless it contained far more mass than what was visible. Using only a handful of measured galaxy speeds and the best distance estimates of his day, Zwicky calculated that the Coma cluster needed hundreds of times more mass than could be seen in stars and glowing gas. He called this missing substance Dunkel Materie, or dark matter. The numbers were startling. The mass-to-light ratio he derived was about 400 times what was expected from visible matter alone. Yet most colleagues doubted his results, blaming measurement errors, mistaken cluster membership, or flawed assumptions about equilibrium. Zwicky's reputation for bold claims and a combative style made it even easier for others to dismiss his warning. For decades, the idea of invisible mass in clusters remained on the margins, waiting for new instruments and better data to test whether the cosmos really was heavier than it looked. By the late 1960s, the puzzle of flat rotation curves demanded sharper tools and more precise measurements. Vera Rubin, one of the few women in professional astronomy at the time, teamed up with instrument builder Kent Ford at the Carnegie Institution. Ford's image tube spectrograph was a leap forward. It could amplify faint signals from the outskirts of galaxies, reaching regions where older equipment saw only darkness. With this device, Rubin and Ford set out to chart the rotation of Andromeda, our nearest large galactic neighbor. Their 1970 study mapped the motions of 67 H2 regions, clouds of ionized hydrogen that glow with the birth of new stars across Andromeda's disk. The results were unmistakable. Instead of the expected drop, the orbital speed stayed nearly constant even far from the galaxy's center. The flatness of the curve meant that invisible mass extended well beyond the bright spiral arms. The stars and gas we could see accounted for only a fraction of the gravity at work. Rubin and Ford did not stop with one galaxy. Over the next decade, they applied the same technique to a growing list of spiral galaxies. By 1980, Rubin's team had measured rotation curves for 21 spiral galaxies, spanning a broad range of sizes and brightness. Everyone told the same story: the outer stars moved too quickly to be explained by visible matter alone. The evidence pointed to a vast, unseen halo surrounding each galaxy, containing several times more mass than all the stars and gas combined. What began as a technical achievement became a universal rule. Spiral galaxies everywhere are wrapped in a cloak of dark matter. After Rubin and Ford's rotation curves made the unseen mass in galaxies impossible to ignore, astronomers weighed every alternative. Some argued the mystery could be solved by changing the rules of gravity. In 1983, Mordechai Milgram introduced modified Newtonian dynamics, called MOND, tweaking Newton's law at extremely low accelerations to explain flat rotation curves without extra matter. MOND fit many individual galaxies well, and later Jacob Bekenstein's T-VES theory attempted to extend it to work with relativity and to predict light bending. But these models struggled with galaxy clusters, where even modified gravity required more mass than what could be seen. The problem became clearer with systems like the Bullet cluster, where the gravity map and the visible matter simply did not line up. Others looked for hidden ordinary matter, massive compact halo objects called machos, such as brown dwarfs or faint black holes. Throughout the 1990s and the 2000s, the Macho and Eros collaboration searched for these objects by monitoring millions of stars for micro-lensing events. Their results showed that machos make up only a small fraction of the dark matter in our galaxy. Meanwhile, hot dark matter, for example neutrinos, was also considered. Precise measurements of the cosmic microwave background and the growth of cosmic structure showed that fast-moving particles cannot account for the universe's clumpy web. Each alternative explained part of the data, but none matched the evidence from all sides. The case for a new, invisible form of matter kept growing, and dark matter became the strongest explanation. Gravitational lensing offers a way to weigh the universe without relying on how objects move. When a massive cluster sits between us and distant galaxies, its gravity bends and distorts the background light, creating stretched arcs and smeared images. This distortion reveals the true distribution of mass, whether it glows or stays invisible. The Bullet cluster, cataloged as one E0657-56, became a landmark case, roughly 3.7 billion light-years away. It is actually two galaxy clusters caught in the act of colliding. As they pass through each other, most of the ordinary matter, hot X-ray emitting gas, slammed together and slowed down, piling up in the middle. But the galaxies themselves, and with them the majority of the gravitational mass, sailed through almost untouched. Lensing maps showed that the greatest concentration of mass lined up with the galaxies, not with the hot gas. This separation was impossible to explain with just visible matter or tweaks to gravity. The Bullet cluster stands as direct, visual evidence that most of the mass in the universe is made of something invisible, something that barely interacts except through gravity: dark matter. The modern picture of the universe is built on a cosmic ledger. Decades of evidence from galaxy motions, cluster lensing, and the cosmic microwave background have allowed astronomers to tally the ingredients of everything we see and everything we do not. Ordinary matter, the atoms that make up stars, planets, and people, accounts for just about 5% of the universe's total energy budget. Dark matter outweighs it by more than 5 to 1, making up roughly 27%. The rest, nearly 68%, is dark energy, a mysterious force driving the universe's accelerated expansion. These numbers come from precise measurements of the cosmic microwave background by satellites such as Planck, which track how early fluctuations grew into today's galaxies and clusters. The search for dark matter's true nature now stretches across the globe and beneath it. Deep underground experiments like Xenon and Lux use tanks of liquid xenon to look for rare collisions between dark matter particles and atomic nuclei. Particle accelerators such as the Large Hadron Collider hunt for new particles that could explain the missing mass. In space, telescopes map the subtle bending of light, weak gravitational lensing across vast cosmic webs. The Vera C. Rubin Observatory in Chile is entering its commissioning phase, preparing to scan the sky with a 3.2 gigapixel camera. Over the next decade, it will chart the shapes and positions of billions of galaxies, turning their tiny distortions into detailed maps of dark matter's invisible scaffolding. The universe, once thought to be defined by what shines, is now known to be shaped by what does not. The hunt continues, with every new observation sharpening our view of the hidden majority. Most of the universe's mass remains invisible, yet its gravity shapes every galaxy, every cluster, and every future discovery. As the Vera C. Rubin Observatory begins mapping billions of galaxies, the search for dark matter pushes science to its edge. The cosmos is stranger and richer than anything we can see.